Hi everyone, this is the second section of Chapter 1. It's titled Linear Measure, and we're going to be talking about segments through this section, specifically how to name them, how to measure their lengths using a ruler, and also how to calculate lengths. So that's really the focus here of this section. Starting out with vocabulary, a line segment. So over here on the right we have a line segment. We know a line segment has a beginning and an end. Unlike a line, it does not go on infinitely. So you can consider this line segment starting at point A and ending at point B, or vice versa, starting at point B and ending at point A. So I guess we could say it has a finite length. And the way we notate that is we say AB, we use, actually I should mention, these are called endpoints. And we use those endpoints to name the segment. So we can say that this is segment AB, and we're going to put the bar over it. We're not going to put the arrows as we would using a line. But you could just as easily call this BA. So the order doesn't matter. And that's how you notate a line segment. Congruent is a word, adjective that we use to describe specifically to segments equal measure or equal length. And congruent does translate specifically to equal measure. So we'll be using that to talk about angles as well. We'll use it to talk about different shapes like triangles, etc. So equal measure. So congruent segments would be equal length. And the symbol for congruency is an equal sign, and then it has this squiggle called a tilde over it. So we'll use this symbol all year long. And over here to the right we see a segment AB is 1.7 centimeters, and a segment CD is also 1.7 centimeters, so they have equal measure or equal length. And so we could write that as AB. Segment AB is congruent to segment CD. And that's how we would write that symbolically. Betweenness of points, or the word between in geometry, this is very specific, and actually let's even write this down. It's a precise description. In the English language, between is quite vague. We could say that one person is standing on one end of a room and another across the room, and you could describe maybe any other person as between them, somewhere else in the in the room, somewhere between them, and that's kind of vague. But in geometry, betweenness or between is very precise meaning. So if you would look over here in the diagram, we could say that this point M is between points P and Q. So what does that mean? First of all, it means that, actually I'm going to write this out. So point M is between points P and Q. And what does that mean? It means precisely that number one, points P, M, and Q are collinear. Okay, so that's the first thing. And the second thing is that M is somewhere in between them on the same line, obviously collinear. So point M is somewhere in between. Now, it does not mean that M is in the middle. So I do want you to write that out. Middle, no. That is not true. Does not mean that M is in the middle. It means it's somewhere on the line in between points P and Q. It could be close up here to P. It could be close over here to Q. Could be anywhere in there. But the word between does not necessarily mean the middle, so that's very important. Now, to calculate a segment length, I'm going to use the same diagram here, and I'm going to use very specific language in geometry. So point M is between points P and Q, and I'm going to use an abbreviation for if and only if. If and only if is abbreviated IFF. I'm going to put it in here. If and only if. If and only if segments PM plus segments MQ equals segment length PQ. Now, this may be obvious to some people and maybe not to others, but what did I just write here symbolically? I basically said that this length, PQ, the whole segment length, is the sum or equal to the sum of its parts. So you'll hear me say all year long the whole is equal to the sum of its non-overlapping parts. They can overlap. If we had a piece of string, for instance, that was this length, PQ, and we just cut the string right here at point M, then obviously if we line up the strings here, it would equal the original length of PQ. So this has a name, and this is called the segment addition postulate, and you do need to know this. Okay, segment addition postulate. And it's all capitalized because it's a proper name. And the segment addition postulate really just means, in the context of segments, that the whole segment, and I'm going to put this in quotes, the whole segment length equals the sum of its non-overlapping parts. All right. And we'll use that same sort of concept with other shapes as well, besides just segments. Okay, now to measure a segment length. To measure a segment length, we would use some sort of ruler or tape measure. And measuring anything comes with inherent error. So we could make a mistake measuring something, so there's always going to be slight error. If you wanted to measure some small segment length, then you need to use a unit that's appropriate for something small. In my course, when we measure or construct things, we will always use millimeters. So I want you to write that down on your notes. Somewhere here near the ruler, I want you to write down that in our course, Honors Geometry, when we construct things and we take measurements, we're always going to be using millimeters. Now, there are a few cases where we actually do some labs outside, and we're going to be measuring things at great distance, in which case we'll tend to use feet or maybe inches. But in the classroom, we'll always use millimeters, so please write that down. Now, looking at this ruler here, the top part of the ruler here, whoops, I'm writing, is inches. And you could see that our ruler kind of goes out to maybe a little bit over 3.5 inches. This bottom portion here is centimeters, and these are exactly the type of rulers we use in class. Now, centimeters, sorry, I ran out of a little bit of room there. I'm going to erase that. Centimeters and millimeters are part of the metric system, and that's a base 10 system. You should be well aware of that. And each one of these here is a centimeter. So, whoops, I've got a centimeter, and it looks like it's going just past I don't know, 9 centimeters here. So if I drew some kind of segment, and I'm going to go out maybe to there, and I called this, I lined up endpoints here, let's call it A, B again. And I told you I want you to measure AB in millimeters. Millimeters are the very small scale here. There are 10 millimeters in every centimeter. So if we looked at this, I could say that AB is approximately, because there's always going to be error here in our measurement, I would say by my eyes maybe 6.4 centimeters. And of course, base 10 system, that would give us 64 millimeters. And the units of measure are, you should always use units of measure that are appropriate for the size, and that has to do with accuracy of measurement. So, looking at some examples here, find the length of AB on example number 1 in both millimeters and centimeters. It looks like AB here is approximately, in millimeters, I would say by my eyes about 42, 43-ish millimeters, and that is approximately 4.2 centimeters. Now let's take some practice using the segment addition postulate. Point Y is between. Again, that is not vague in geometry, that is very precise. Point Y is between X and Z. Find the length of XZ. So we're going to write down the segment addition postulate. I'm going to abbreviate here. So for that, if Y is in between, then we can immediately say XY plus YZ equals the whole, XZ. Now, I'm trying to be very careful in the notes to use the bar over the segments. You and I will probably find ourselves getting a little bit lazy through the year, and maybe we don't always write that bar. It's very good to notate a segment versus a line, so I'm going to try to be careful in the notes to do that. So now we're going to substitute. XY, the length of XY is 4 5/8, and the length of YZ is 2.5 inches, and that equals XZ. So now we're just going to add. We've got 6 plus 5/8 plus 1/2 is going to equal XZ, and I'm going to simplify that. How do I add fractions? Well, I've got 6 5/8, and I'm going to represent 1/2 as 4/8. So I've got 6 9/8. Of course, 9/8 is greater than a whole, and I'm going to add that 1 whole to the 6 to get 7, and my remainder is 1/8. When you get to this point, make sure that you always finish up with whatever appropriate units are in the problem. Okay, point M is between L and N. Find the length of LM. Now in this case, we're not finding the whole segment length, we're finding one of the non-overlapping parts, but we're always going to start with the segment addition postulate. If point M is in between, then segment LM plus segment MN is going to equal the whole, which is LN, and substitute. We don't know what LM is, but we do know that MN is 2 6/10, and that the whole is 4. So I'm going to subtract 2 6/10 from both sides of the equal sign. We might as well do that out. I will not be showing these steps always, however, and LM equals 4 minus 2 6/10 would be 1 4/10, I guess, and our units are centimeters. So that's our answer. All right, moving on to example number 4. Point R is between W and y. In this case, we don't have a diagram, so we have to draw one. So remember, r is in between. So we are going to sketch r in between w and y. So I'm going to make some kind of segment here, w, y. R is somewhere in between. Right now I have no idea. Is r closer to w? Is it in the middle somewhere? Is it closer to y? I don't know. I'm going to just start with a sketch, and then I'm going to label my sketch. Find the length of ry if wy, so we're told the length of the hole here, wy is 19 3/10 millimeters, and wr is 8.7 millimeters. Segment addition postulate always. So wr plus ry equals the length of the hole, wy. Substitute. wr is 8 7/10. We're looking for ry, that's our unknown that we're trying to solve for, and wy is 19 3/10 millimeters. If I'm trying to isolate or solve for ry, we're adding this 8 7/10, so we're going to subtract, would be the inverse operation. Subtract 8 7/10 from both sides. Of course, when we do that, we reduce that to 0, and we now have ry isolated. And ry equals 19 3/10 minus 8 7/10. I'm going to do that over here. I'm going to have to borrow. And 13 minus 7 is 6, and 8 minus 8 is 0. So we end up with 10 6/10, and always put your units millimeters. Again, example number 5, we do not have a diagram, but we're told that point T is between points S and U. So we have to sketch some kind of diagram. S and U, and point T is somewhere in between them. That means collinear. If and only if the whole length equals the sum of its parts. That's really what the segment addition postulate says. Okay, it asks find the value of x, st, tu, and su when st equals 7x. So we're going to label our diagram here, st equals 7x. And su, the whole, equals 45. And tu equals 5x. I've run out of room, so I'm going to put up top here, 5x minus 3. Segment addition postulate, st plus tu equals the whole, su. St, we're going to substitute. We're told that st is an algebraic expression, 7x. Tu is 5x minus 3. And that equals the whole, which is 45. Combine like terms on each side of the equal sign. 5x plus 7x is 12x. Minus 3 equals 45. Okay, we're going to go to the unknown. The unknown is being multiplied by 12. It's being, we're subtracting 3 also from it. And just as a reminder, as we isolate that unknown that we're trying to solve for, we're really working from the bottom of order of operations, or PEMDAS, up. So we have multiplication, we have subtraction. We're going to undo that subtraction first. So inverse operation of subtraction is addition. So we have 12x. Of course, opposites reduce to 0, and 48. And the unknown is being multiplied by 12, so we're going to undo that with division, the inverse operation of multiplication. And any number divided by itself reduces to 1. And so we have x equal to 4, so that's important. Now, as we substitute in x equals 4, what do we get? Well, st would be 28, or 7 times 4 would be 28. And 4 times 5 over here would be 20. 20 minus 3 would be 17. So at this point, it's a really good idea to check your answer. Does 28 plus 17 sum to 45? And it certainly does. So that's a really good approach to always checking your answer, because everything should work out here in your summation. Okay, last problem. Point B is between A and C. So we're going to always do our sketch. Point B is between A and C somewhere. I'm just going to put it somewhere here. Okay, find X, AB, BC, and AC when AB equals 2x plus 14 and BC equals 6 minus 3x and AC equals x squared minus 2x. So we have algebraic expressions for all segments, the whole as well as the parts. Okay, always start out with segment addition postulate. AB plus BC is going to equal the length of the whole, AC. Substitute. AB is 2x plus 14, and BC is 6 minus 3x, and AC is x squared minus 2x. Let's combine like terms, kind of simplify things here. 2x minus 3x is negative x, negative 1x, and 14 plus 6 is 20. And over here we have x squared minus 2x. So we've combined everything on each side of the equal sign that we can. Now, hopefully your eyes are starting to see that we have a term that has an exponent of 2 on it, as well as x terms. So this is what we would call a quadratic, and what we want to do is solve a quadratic equation. Now, you should have studied this last year, but I'm going to quick review. So we're going to solve a quadratic equation. How do we know this is a quadratic? Quadratic takes the form of ax squared, a is just a coefficient, plus bx, b is just a coefficient, plus c. And to solve that, you want to get everything on one side of the equal sign equal to 0. And I do have, oops, I dropped my pen. I do have a video on reviewing all the quadratics, so I can't go into everything here involving a quadratic. But mainly, we will either try to factor this side here of the equal sign in order to solve easily, or if it's not factorable, meaning that the solutions for x are not simple fractions or integers, then you would have to use the quadratic formula. In this case, let's see what we have. So I'm going to try to get everything on one side. I'm going to rewrite it over here. 20 minus x equals x squared minus 2x. Since I have a positive x squared over here, I think I'm just going to go ahead and move everything over to the right. So I'm going to subtract 20 from both sides, and I'm going to add x to both sides. Those are the inverse functions. So 20 minus 20, of course, is 0, and the negative x plus x is going to be 0. So that's my goal. Get 0 on one side of the equal sign. So I have x squared. Negative 2x plus x would give us negative x. And I'm just got negative 20. So let's see if we can factor this quadratic here. So what do we have? What we want to do here is multiply a times c. And a in this case is a 1, invisible 1. So we have negative 20. And what we're looking to do is rewrite this middle term, this x term, using this product of a and c here, negative 20. So we're looking for, I like to draw a little table here. We're looking for factors of negative 20 that sum to this coefficient here in front of the x term, this coefficient b. So we want to get a number where we sum these factors to this negative 1. So what can we get? Well, we've got factors of negative 20, we've got negative 5 and positive 4, or we could have positive 4 and negative 5. We could have, by the way, negative 10, positive 2, negative 2, positive 10, etc. But the very first one I chose sums to negative 1. Negative 5 plus 4 is negative 1. This would be, oops, I'm sorry, I rewrote the same exact thing here. I meant to write positive 5, negative 4. You can see that sums to positive 1. So we're looking for this combination here. And so we're going to rewrite that middle term here. We've got, I'm going to flip it all over too. I've got over here x squared minus x minus 20 equals 0. And we're looking to rewrite this. And we're going to rewrite that using our factors over here. So I'm going to say x squared. I'm going to rewrite negative x as minus 5x plus 4x. So I didn't change that left side of this equation. I just rewrote that negative x term as the sum. Now we're going to factor, it's called factor by grouping, and we're going to factor the greatest common divisor out of the first two terms and then the greatest common divisor out of the last two terms. Hopefully you can see that the greatest common divisor out of x squared and negative 5x is just x. So I'm going to take that x out. It's kind of like using the distributive property in reverse. Whoops. If I divide x squared by x, I just have x. If I divide negative 5x by x, I have just negative 5. Now so hopefully you can see that this is the reverse. Factoring is the reverse of distributive property here. If I multiply that x back through and I distribute it using the property, then I would end up with x squared minus 5x again. So I'm just rewriting equivalent expressions, if you will. Hopefully you see that the greatest common divisor out of the next two terms is, let's say, 4. So I'm going to say, I want to go back to red, I'm going to factor that out. 4x divided by 4 is just x, and negative 20 divided by 4 is negative 5. And hopefully you see here that if it is factorable, if this quadratic is factorable, you're going to see that we're going to end up with the same term here, x minus 5, x minus 5. And both x and positive 4 are multiplying the same entity or the same expression. So we can then further simplify this as x plus 4 is multiplying x minus 5 because both of those quantities, if you will, are multiplying that term x minus 5. Now when you get this far, you can just take each one of these factors equal to 0 separately, independently. And here we're going to subtract 4 from both sides, so you end up with x equals negative 4. And over here we're going to add 5 to both sides, so you end up with x equals 5. Now both of these values for x are perfectly correct for an algebraic problem. So they are correct algebraic solutions for x. But they may or may not be correct for our geometric problem. And there's only one way to figure out whether they are, and that's trial and see what you get. So we're going to substitute, and we're going to go back over here to our algebraic expressions. If we square, let's start with a positive one first. If we square 5 here, we get 25 minus 2 times 5. So that would be 25. Actually, I'm going to make a nice table. Why don't we do that? I've got an expression here. Got several. So let's try, this is always a really nice approach, is create a table. So we've got 2x plus 14, we've got 6 minus 3x, and we have x squared minus 2x. And just go ahead and substitute. So 2x, we started out with 5 being squared here. That's 25, and minus 2 times that would be 25 minus 10. So we would end up with 15 here for the whole length. Now if I have 6 minus 3 times 5, that's 6 minus 15. So that would give us a negative value. 6 minus 15 would be negative 9. And 10 plus 14 would be 24. Now 24 minus 9 is 15, but we cannot have a negative segment length. It just is not possible. So x equals 5 is not a geometric solution. It's a perfect algebraic solution, but not a geometric solution. So let's take a look at our negative value here, negative 4. And I'm going to start out with the whole. So negative 4 squared is negative 4 times negative 4. That's 16. 16 minus 2 times a negative number would be 16 plus 8. So 16 plus 8 would give us 24 here. Likewise, 6 minus 3 times this negative number would be 6 plus 12, or 18. And 2 times a negative 4 is negative 8, plus 14 would give us 6. So now we can check this out and see, does this add up? Does 6 plus 18 give us 24? Well, it certainly does. So there we've calculated out all of our values here. X does equal negative 4. AB equals 6 units. And we were not given a particular type of units like inches or millimeters, etc. So we would just, in this case where we don't know what the units are, you would just write out units. So we've got x equals negative 4, AB equals 6 units, BC equals 18 units, and the whole AC equals 24 units. And that's how we would write our final answer. Thanks for listening.